So if we're comfortable with patterns as being a kind of repeating set of action across elements, right? And if we're talking about grids plus influence plus action, all we've done thus far is make simple grids. We've decided that the influence is either going to be, let's say, a kind of on-off switch or a repeating collection of scale values. And then the actions then will have been keep or remove in the first example. And the second example, how big do you want your circle to scale? All right, so we're going to kind of shift now, if we're comfortable with things that repeat and kind of different objects across a grid of points, into fields, right? And we'll be talking about fields of influence. All right, so here we have a representation of a couple of fields relative to how they're represented in physics studies, right? So here we have two influencer objects, let's say, that are creating this color wheel describing direction, that are actually oriented in opposite directions to each other, so you get a kind of merging, right? And color is a really good way to be able to understand fields across this entire plane. Here we have objects that are oriented in the same way, and the resulting field in between, you can see, is different than down here. Okay, so a field is really, in the most simplest sense, a continuous space characterized by diminishing influence over distance. All right, so a continuous space. All right, so it's kind of an ever-expanding plane, let's say to start, just a plane. So all the way in the UK versus here in New York versus out in California, right? A continuous space, right? And if the individuals that are participating in the webinar from those locations, right, if we think about them as having influence over the world, right, but that influence decays as you move away from them in their geographic location, we now have a field. And fields are really convenient because they can be sampled at any position. Aside from where the influencers are, UK, New York City, or California, any location, anywhere can be sampled, and we can get information back from that field. Okay, so here's a kind of simple diagram that describes an electromagnetic field, right? We've probably all, at some point, played with magnets, right? And if we have a positively charged magnet and a negatively charged magnet, these curves describe how there is influence being acted upon anything that is in this continuous space, right? So if you have a metal filing here, it's going to be influenced by the electromagnetic field based on these two influencers, right? And as you go farther away, of course, that influence diminishes. Okay, and the things that we're going to be calling what the influencers are in our field are going to be charges, right? And that's just a generator of local influence within a field. Okay, so here's another way to represent a field, right? A field is invisible, let's say, but at any point within the field, we can query that field for values, right? In this case, these are scalar values that exist between two extremes, right, and are represented by purple. Sorry, a spectrum from purple to green back to magenta. Right, so this is a scalar field, right? These are just numbers that we're returning that are describing influence. And beyond scalar, there are also a couple of other ways to preview fields. You can create a color map that's based on the direction of the field, and you can also create a collection of vectors that describe the tensor at that location. And we're going to get into what exactly those are and how they look as we bounce back over into Rhino. Okay, so let's open up the next file. This is fields of influence. Okay, and this is where we're going to go, right? We're going to end up with a collection of different previews that allow us to understand a field of influence from some charges, right? So here we have this is pretty similar to the physics diagram I showed you of the color spectrum. All right, so this is direction display of our field. We have scalar preview of our field, right, which is kind of like a heat map. And then we have the tensor preview. And the tensor is the vector that's describing the difference at that point in the field between all the influencers, right? So here you can kind of think of these as metal filings that are getting reoriented based on the charges in the field. So we're going to go back through, again, what all of those things mean once more as we build up our file. All right, so let's go ahead and save as a working file. And let's go all the way back to our triangular grid, and we'll delete all of this. All right, so we should be left just with our triangular grid, right, which just has the same inputs we've been creating thus far, EX, EY, and is giving us our grid cells and our points. Okay, so let's bounce to the Vector tab. Next to the Grid tab, you'll see that there are these objects here under the Field sub-tab. And the field objects are new to Grasshopper version 9, I think. And these are really great because it allows us to start to think about fields and causing influence across a continuous space with very, very easy controls. All right, so you can see here there's a number of kind of force objects. We'll call them all of those things that are in the first four first four objects here in the first section. There's a line charge, a point charge, which is kind of like our magnet, something that causes spinning, and a vector force, right? These are all the different kinds of charges you can place within your field. And then next we have a couple of options that allow us to bring fields together. If we have two magnets, what do? Well, we merge those fields. A couple of objects that allow us to evaluate any location within the field. And then our last category is all about how we might preview the field, right? What we get as a result. Okay, so the first thing we want to do is we want to create some charge locations. So let's go ahead and drop a point object in Rhino somewhere where our triangular grid is. Any place is good. So I've got now a single point in my top view located near my triangular grid. All right, and what we're going to do is we're going to use that point to create our first charge, right? And that's going to create our local influence within the field. Okay, so let's go to the params object tab and grab the point object from the geometry subtab. All right, this is our point container, and we'll label this as charge point. Okay, let's go ahead and right-click, and let's store that point in this container by setting one point. All right, so now we've got that point selected. We should have a little red crosshair on our viewport that shows us the location of the charge point, and we can move it around in Rhino as we want. Great. The next thing we're going to do is we're going to take that point, right, which is just a location, x, y, z, and we're going to turn it into a charge, right, which will actually cause influence in our field. So let's go back to the vector field subtab, and let's grab our point charge object. Create a field due to a point charge. All right. So we'll drop our charge point into P, that is the location of the point charge. You'll see that the preview changes. This is not just a location in space. It now also has these arrows associated with it, which are having to do with how it's understood as an object that's causing influence, right? So that's the icon that is shown on the preview for our charge object. You'll see here that there's also a value you can specify for the strength of the charge, the decay, and the optional bounds for the field, right? Now we're going to leave all of those as defaults. One quick note, I've experienced some very weird behavior from supplying a value to D, so I don't recommend that you specify anything here because it's caused lots of crashes. That's something that we've talked with David Rutan about, the developer of Grasshopper. I think it's on the to-do list. But you can work with the charge by specifying kind of how strong that charge, or if you're thinking about them as magnets, how strong that magnet is. Okay, so I'm going to leave them as default, all those inputs as defaults for now. And let's go ahead and let's start to preview the corresponding field. All right, so there's a field that's created from that charge point, but we just can't see it, right? It's invisible until we actually represent it in a particular way. So we'll go back to our Vector Field tab, and let's start by looking at the Tensor Display, right? These are the tensor vectors of a field section. So we're actually having to section the field, right? The field is continuous in all three directions. So what that means is that there's influence in the z direction as well as xy, even though we've just located that point on the xy plane and we're working with a grid. So basically we have to create a section at the xy plane in order to understand how that field is, what the values are in that field at that location, right, in space, because it's continuous in all three directions. Okay, so let's go back to the field subtab, and let's start with tensor. All right, so let's grab the tensor display, and this asks for the field that we want to evaluate, the rectangle describing the section, so that we're going to have to somehow find a rectangle here, and n is the section sample count indicator. So that's to what degree of resolution do we want to sample our section of the field. All right, so let's start with f. What's the field? Well, that's going to come from the charge object, right, the result of the charge. So the charge creates a field. Okay, s, this is the rectangle describing section. Okay, so now somehow we need to actually get the section that corresponds with our original grid. So we need a rectangle object, and one way to do that would be to take our triangular grid and let's see if we can get the bounding rectangle of that grid. So we're going to have to go to the Surface tab, and we're going to use a bounding box as a way to understand where what the bounding rectangle is of our entire collection of grid cells. So let's grab the bounding box. This says what geometry do you want to contain and what is the orientation of the bounding box on a plane. So the world XY sounds good. So we're going to take the geometry to contain is going to come from our grid cells. Okay, now we have a couple of issues we have to deal with. When I do that, this gives me 680 bounding boxes. I don't want 680 bounding boxes. I want one bounding box. So there's a couple of things that we need to note. And if we look at the preview of our objects here, there's a couple of the two things that we need to modify are going to be related to, one, the fancy wires and how it's describing what's going through that wire, how the data is organized. And the other is this label if you zoom in. On some objects in version 9, now you have a visible a label describing how this is working. So this is saying per object. It wants a bounding box. It wants to make a bounding box per object. And that's probably not what we want. We want one bounding box for all of the objects. So let's take care of that one first, and let's right-click and say, instead of per object, we want a union box, which says a single box for all items in each list will be returned. Okay, so that helps us in one way. Instead of 600 and some boxes, now I only have 40. And we're one step closer because now we have 40 bounding boxes, but we still only want one bounding box, right? And what's happening here is we have a collection of grid cells, and they're organized in a data tree, which means that on each list, we're going to get one bounding box as a result. So that's not something we want, right? We want all of these grid cells to be understood as one collection. So if you've right-clicked and specified union box here on the bounding box object, then you should be able to then make one more modification to get one box as opposed to 40 boxes. So if you have a suggestion on how we might do that, go ahead and type that into the question window. All right, you got it. Flatten. We need to flatten the C input by right-clicking, saying flatten, and now we get one bounding box. And if we put our mouse over B as an output, it says it's a flat box. That makes sense, right? Because our grid cells, they're just lines that are on the XY plane. So there's no depth to our box. There's a width and a height, but no depth. And that's okay. All right, so the next step is we need to go from a bounding box back to the actual rectangle that describes the edge of that bounding box. So if we stick with the Surface tab and we look under Analysis, there's a B-rep wireframe object here. And that gives us the wireframe of our box. So let's drop that into the canvas. We're going to connect B to B, and this is going to give us 4 lines, right? It's going to give us the bounding box edges as 4 lines. Now, does anyone want to take a shot at describing what a B-rep is? Okay, B-rep. We have one suggestion, polysurface. Yes, that's correct. That's another way to describe a B-rep. A kind of envelope, right? That's also pretty close. The B-rep stands for boundary representation, and relative to Rhino, it is when you're creating solids or objects that are composed of multiple surfaces as a way to describe a kind of boundary, right? So if you had a box has 6 faces. In Rhino, each one of those faces is one surface, and when they're joined together, we get a B-rep. All right, so we now have the wireframe of the B-rep, which is just the 4 edge curves, and we need this to be understood as a rectangle. So let's take these 4 edges, these 4 curves, and let's join them together into one closed polyline. So if we go to Curve, Utilities, Join Curves, and as a result, we now have one polyline curve. Okay, now that polyline curve is what's going to go into the section input for our tensor display. Okay, so I'm going to go back through and make sure that I group this. Go ahead and make sure that you have this set up appropriately, and that your previews, that you've only got the charge and the tensor object previewed. Everything else should be previewed off. So this was our bounding box. This is our B-rep wireframe. Join curves. This was our charge, point charge. And this is our preview. We'll call this just preview, even though it's giving us tensors. So this kind of makes sense, right? If these are metal filings on a table and you have a magnet, the metal filings are going to get oriented in the same direction as our vectors here. And again, these are called tensors. A tensor is anything that describes difference between 2 things, right? Now we have 2 things, right? We have a location in space and a charge, right? In this case, only one. But if you relate the position in space to the charge, the tensor is the result preview. This previews the result of that difference between the point and the charge, right? Which of course is decaying over distance, right? So the tensor is just showing us directionality, but there are a number of other ways for us to preview our fields. So let's go ahead and turn the preview off of the tensor, and let's add in the rest of our preview options. So again, let's go back to Vector, Field, and let's grab Scalar Display and Directional Display. All right? This is going to share all the same inputs. So F is the field that's going to go into those F inputs. These are our sections, S, here and here. Okay, so if I look at just the scalar display, right, I get a kind of heat map, right? Or I guess kind of weirdly an inverse heat map, right? It's yellow here near the point charge, which I can move around, and of course my preview updates, and more red away from the point charge. All right, and that's giving us a kind of, if this were a heat source, right? One easy way to understand this preview is that as we move, again, the colors are kind of funny for this analogy, but as you move away from it, the heat source is diminished. So it's less hot here than it is hot here. Right? Similarly, if we turn the preview off of this one, which was scalar, and we go to this option, which is direction, turn the preview, here we have a color wheel, a radial color wheel, that shows us the kind of directional influence within the field. All right, now these are pretty simple, color previews that we're getting, right? So if we want to start to work with something that's a little bit more interesting or more complex, all we really have to do is start to specify more options for what kind of charges we use, right? Or at the very least that we have more charges. Okay, so before we go any further, I'm going to select these objects and make sure I add them to the preview group by right-clicking and say Add to Group. So now they're a part of the preview, right? And